intervals when the function's increasing and decreasing. So the example we're going to look at is g of x is going to be equal to x squared minus x minus 12. Okay, so if we want to find local extrema, we know we need to find critical points. So to find critical points, I'm going to take the first derivative. First derivative is going to give me 2x subtract 1. And then we know that we have critical points where the derivative is either undefined or equal to 0. So I'm going to set 2x minus 1 equal to 0. So I'm going to say 2x is then equal to 2. So then x is equal to, 2x is equal to 1. That's a 1. So x is equal to 1/2. So that means we have a critical point at 1/2. And we need to look at what's going on in the first derivative to the left and to the right. So I might look at first derivative, what's going on at 0, and then I'll look at what's going on at 1. Okay? If I plug 0 into the first derivative, I get negative. And if I plug in 1 into the first derivative, I get a positive. Okay, so now we can tell that we're going to have a negative derivative because the tangent line is going to be negative, and then it's going to be positive. So that's going to give us a min here at 1/2. So that answers our first question. We're going to have a min located at 1/2, and in order to find the y value, we're going to plug 1/2 into the original function. And if I plug 1/2 in, that'll give me negative 12.25. Okay, now I'm going to move on to where the function is increasing. Well, we know the function is increasing from the mean value theorem whenever the first derivative is greater than 0. Okay, when the first derivative is greater than 0, we're going to have our increasing functions. So where it's positive over here is going to be at 1/2, and you're going to go interval all the way over to infinity. Now, I've seen our textbook, and hopefully not Math Excel, but I've seen our textbook put brackets here, and former students have looked this up and we've researched it, and we are convinced that this should be not including 1/2 because that's a critical point. The function is not increasing at that point. But if Math Excel includes that point, then we don't think that's correct. Okay, and then C, we're going to look at where the derivative is less than 0. So that's going to be where the value is negative. So I'm going to go from negative infinity to 1/2. And again, we're not going to put a bracket. We're going to put a parenthesis because it doesn't include 1/2. Okay, on the next page, we're going to talk about a new term, which is called the antiderivative. And basically the antiderivative is whenever you're given a derivative and you're asked to find the function. So you're going to be working backwards. Okay. Antidifferentiation is the process of finding a function given its derivative. Again, that backwards process. We've done differentiation, and so antidifferentiation is going to be working backwards. Okay. We know that a function if it has one antiderivative, if a function has one antiderivative, then it has infinitely many antiderivatives. So let's look at an example here to explain this last concept. So let's say that we know that our derivative is the sine of x. Okay? If we work backwards, which is the process of antidifferentiation, is to work backwards, then we're going to come up with what f of x is. Okay, so f of x, if I think about this, what function is going to have a derivative of sine of x? Well, that's the negative cosine of x. Okay, because if I take the cosine of x, it gives me negative sine. If I take negative cosine, then it's going to give me positive sine of x. Okay, so this is the antiderivative, negative cosine of x. But here's where it comes in, why we have infinitely many. So if I take a constant and I add a constant over here, let's say I add 1. If I add 1 to this, the derivative of this function is still sine of x because the derivative of 1 is 0. Okay, so this is an example of another antiderivative of this function. Okay, I could also add 10. Same thing. I could add any constant over here. So any constant. Okay, basically each each antiderivative will differ by a constant. Okay, so we can just put any constant in there. It could be -10, could be any value in here. It's going to differ by a constant. Okay, now we're going to have two corollaries. Corollaries, again, are statements that they can't stand by, or they're so dependent and so related to another theorem that we're not going to give it its own name. So it's going to be a corollary to the mean value theorem. These are very important concepts that are going to come help us with as we move into integration. The only functions with 0 function as its derivative are constant functions. Okay, so let's look at exactly what this says. So, or let's look at an example to put this into context. So the only functions with 0 as its derivative. So let's say 0 is the derivative. Okay, if I take the function, it's going to be, like, say I take a constant of 5, the derivative is 0. The only functions that have 0 as a function are constant functions. So this right here are your constant functions. Okay, the next theorem is, again, the mean value corollary. If two functions have the same derivative, then they differ by a constant. Okay, so if two functions have the same derivative, then they're going to differ by a constant. Okay, so let's think about what that means. This is similar to what we just worked with. If I say, let's say I have a derivative of f of x equals 4x. Okay, so I'm going to work backwards, and I'm going to come up with, if two functions have the same derivative, okay, let's say the antiderivative could be 2x squared plus 4. Okay, I'm going to come up with another function that's going to have the same derivative as this one. So I'm going to say f of x is equal to, let's say, 2x squared minus 6. Well, the derivative of this is 4x. Okay, so both of these are the different functions. They differ by this constant value right here. Okay, they differ by a constant. So this value is 4x, this derivative is 4x, but the constant is different. The only thing that's different about the function is the constant, but the derivatives are the same.